Okay, hi, I'm James. Today, this talk will be on total outcome logic, an extension of the theory of outcome logic, which adds additional support for reasoning on termination and non-termination. So, just to begin, why don't we start by considering what outcome logic is and its particular vision in the entire landscape of program logics in general. So, so the entire landscape of program logics consists of a range of specialized theories which are tailored which are tailored for particular modes of reasoning, as well as particular computational effects. So we have the archetypical Hoare logic and its correctness logics that were developed thereafter. We have probabilistic logics. We have the recent body of incorrectness logics, which shifts focus from analysis for verification onto bug finding. So what outcome logic seeks to do is it seeks to unify this landscape through a single theory under a single meta-theory. And this unification takes place across two main fronts. So outcome logics generalize over branching effects. So for example, they can be instantiated for programs that exhibit non-determinism, as well as those with randomization, for instance. And in addition, outcome logic captures both correctness and incorrectness properties, and this makes it particularly powerful in serving as a theory that can both perform verification and bug finding. But despite this, there are some limitations, in particular when it deals with the effect of termination and non-termination. So outcome logic is unsuitable for proofs of total correctness, as you might see in total Hoare logic with the variant inference rule. It also struggles with proofs of the existence of non-terminating executions. And this is a direction of work that has seen much more attention in the incorrectness sphere with the development of a logic like unter. So to paraphrase, we want to be able to ask, does my branching program surely terminate across all its branches? And is it possible that the program fails to terminate in one of its branches? So these cannot be answered in outcome logic. Instead, we propose a simple extension of this, of the theory of outcome logic, to provide support for proofs of these kinds. So, but before we actually delve into the framework, why don't we consider what would be an adequate semantics for modeling program behavior in our case? So a lot of this will be review of vanilla outcome logic. So one of the first promises we made as regards to outcome logics is that it can generalize over branching effects. So that means like programs that exhibit probabilistic branching. So take, for example, this very simple program of a fair coin flip. How would we go about representing the results of running this program? Well, we know that this program branches into two outcomes, each of which occur with a probability of 1/2. Or in other words, we can specify the result of running this as the set of its possible outcomes, along with labels, along with weights that are assigned to each of these outcomes. So in this case, these would be the probabilities. But if we carry this thought over to non-determinism, well, we can see that the most intuitive way to represent the result of running this program is to just provide the set of outcomes that are possible. And it turns out it's pretty easy to see that this is basically another instance of our weighting scheme, as discussed before, where, again, we have a set of outcomes, but now our labels or our weights are drawn from this trivial set of values of either true or false, where true indicates that a particular outcome is possible, and false indicates that it isn't. So we seem to have stumbled upon a common structure that we can use to construct our semantics on. So the fundamental idea is that we want to model program results as these maps from a state space to a set of weights labeling each outcome. And we will call these types of maps weighting functions. And to formalize weights more rigorously, it turns out that a very nice formalization is to just require that it's drawn from a semi-ring. And this affords us very nice algebraic properties upon which we can build the meta-theory. But in each of these examples, for instance, in the example of non-determinism, we can see that the weights are drawn from a Boolean semi-ring, where the labels are either true or false. In the case of probabilistic programs, we are obviously using a real-valued semi-ring on the 0 to 1 interval. And we find that with just a few slight restrictions on the weighting function themselves, weighting functions end up corresponding to probability distributions in the probabilistic model. So we have accounted for branching effects in our semantics, but now the other effect that we need to somehow encode is that of non-termination. And the simplest way of doing this is to simply encode non-termination as an explicit outcome in our weighting functions. So again, we will be using the weighting functions to weight each possible outcome. But now we expand the domain to also include this additional symbol which stands in for non-termination. So in our semantics, we can see that we can explicitly specify with what weight a program may diverge. Now, the combination of these two effects admits some difficulties, especially as we try to formalize the denotational semantics. I will omit the mathematical details, so this will be very expository. But intuitively, the problem with the semantics is that we have now opened our way up to modeling programs that we may not want to model whatsoever. So in this case, consider this program that non-deterministically sets x to any natural number. So here we see that this program can produce an infinite accountable number of branches in a single step of execution. But as it turns out, it's a classical result in denotational semantics that there is no Scott continuous semantics that captures both this effective non-termination as well as unbounded non-determinism, as we've seen in the previous program. So again, forgoing the mathematical details, perhaps a way of getting an intuition of this is to simply consider this program that consists of the non-deterministic assignment we had before, sequenced with a loop that decrements the value of x to 0. So it makes sense that for any one branch of execution of this program, the program will surely terminate. You choose any natural number to set to x, and the loop will terminate in a finite number of steps. And yet, the view that kind of pops up in the semantics is that if we instead look at this from the perspective of a machine that has to explore every branch of execution, we see that, well, there are an infinite number of branches to explore. And so from the top down, it seems that the entire program does not terminate. So there is this disconnect from viewing this program from the top down versus from the individual branches that it can spawn, a sort of discontinuity. So what this admits now is a pretty straightforward interpretation of programs as maps from an initial state to these weighting functions that we just introduced. So in the example of probabilities, you would take an initial state, run your program, and then I would feed you back a probability distribution. So this encoding of non-termination inner semantics now allows us to build artifacts in our actual our logic theory to begin to reason about non-termination and termination. So to actually take a look at the framework, our formulas are, again, these triples, sandwiched by these outcome assertions. But what is particular about outcome logic is that these assertions no longer correspond to simple sets of states, as they would for usual program properties. Instead, they're lifted to hold on weighting functions. So for instance, if I had a probabilistic program, I would have to account for the branching effects by taking my assertions to be collections of probability distributions instead of just sets of states. And it's this lifting that affords us a lot of versatility with outcome logic. So just taking a look at our assertion language, we have the regular propositional core, and we augment it with existential quantification. We have this conjunction, very similar to a separating conjunction that we call outcome conjunction. And then we have these two primitives for reasoning about weighting functions. So to just get an example of these new assertions that we introduce, let's first take a look at this bottommost primitive assertion, where you can think of P as a sort of a program property specifying a set of program states in which the property may hold. And it is lifted with a certain weight from our semi-ring to hold on weighting functions. So in this case, you can intuitively view this definition as any weighting function that satisfies this assertion. Well, the outcomes of this weighting function must satisfy P with a total weight of A. So to get a better visualization of that, suppose we have this property P consisting of these two program states. Then considering this example weighting function, we say that it satisfies P weighted with A if first the non-zero support of this function falls in P. So we can see in the red bars, sigma 1 and sigma 2 are fall in P. And if the total weights add up to the weight specified, which is A. So the next primitive assertion that we have is to support divergence. So this is very, very similar to the weighting of program properties, except here we essentially, any weighting function that satisfies this assertion must diverge with a weight A, and it must only diverge. So this essentially consists of a set of one single weighting function that looks like this. With all the weights on the non-termination outcome. And the last introduction we have is outcome conjunction. So for a weighting function to satisfy outcome conjunction, it needs to be able to be decomposed into a sum of two other weighting functions, each of which satisfies the wings of the conjunct. So to get a better visualization of that, suppose we have this weighting function M, and we say that it satisfies this outcome conjunction. Then we know it needs to be able to be decomposed into a weighting function M1, which satisfies the first wing of this conjunct, added to another weighting function that satisfies the second wing. And an interpretation of triples is follows the usual over-approximate sense, but recall that assertions in this case are lifted to weighting functions. And so as we will see, despite the fact that this interpretation of triples is fundamentally over-approximate, we can capture notions of correctness and incorrectness through it. So just to go through the subsumption of different program logics that can be done in total outcome logic, we know that partial correctness and incorrectness can be captured by outcome logic, whereas when we introduce support for divergence, we expand this to unify the entire landscape, including total correctness, and this naively named partial incorrectness, which augments incorrectness with some notion of divergence, not quite like the unreachability presented just before. So to begin with, let's see how we can encode these modal operators. So we have square p for representing that p always holds, and a diamond p modal operator that represents that p sometimes holds. To encode this as an actual outcome assertion in total outcome logic, we can provide this encoding. Very intuitively, this just says that for any weighting function that satisfies square p, it needs to either, its possible outcomes either fall in p or diverge. On the other hand, for the sometimes modality, we can encode it as such, where essentially we capture a backwards under-approximate notion of incorrectness by seeing whether the outcomes in the weighting function intersect with the property P. So these are the encodings of Hoare logic and the backwards under-approximate notion of incorrectness given by Lisbon logic. And these can be supported in outcome logic proper. But if we take a look at these encodings and we choose to transpose this allowance of non-termination in each of these modalities, we arrive at a slightly different set of modalities that we will represent as such. And what this ends up representing is that P always holds with no allowance of non-termination, and that P sometimes holds, or it may diverge. So just to give a unified view of the subsumption that can be achieved in total outcome logic, we see that with our support for reasoning on divergence, we can capture total correctness and total Hoare logic using this augmented, this alternative square modality, and we can achieve, we can capture a notion of, a different notion of incorrectness in which non-termination is treated as a bug in itself. And so in the case of a logic like Unter, which is specialized to detect non-terminating traces, this is basically just the instance of this diamond modality in which the program property we specify is simply false, by which we just specify that we're only looking for non-termination. Yes, sorry.
Okay, great. We can do one really quick.
I have a remark on the unbounded non-determinism, because you said it's non-continuous. It's not true in general. If you take traces, then the semantic is continuous. If you take relational semantics, it is not. And there is a mystery here that I not fully understand, why this abstraction goes from continuous to non-continuous. So just a little remark.
Okay, let's thank James one more time.